Welcome. Tonight, this video explains why humanity cannot relocate to Venus. Make yourself comfortable, like and save this video, and listen at a calm pace. Now, let us begin. This part defines the task clearly and sets the frame for the entire explanation. Relocation means the permanent and self-sustaining presence of a large number of people on or around Venus. The scale includes families, infrastructure, industry, and reliable services. The flow of people and goods from Earth is assumed to be limited and expensive. A one-time expedition, a short research campaign, or a small demonstration habitat does not meet this definition. Temporary survival is not considered success. The target is long-term stability with margins and reserves. The discussion separates 4 levels of human presence. An expedition is a brief visit with consumables brought from Earth. A base is a small outpost that depends on resupply and can be evacuated. A colony is a larger installation with partial local production, but still under external support. Mass relocation is the settlement of many people who can live and reproduce safely with only occasional imports. The analysis that follows concerns the last case because only it matches the common meaning of relocation. Evaluation criteria are defined in advance to avoid confusion later. Physical environment includes temperature, pressure, atmospheric composition, wind, illumination, and radiation. Biological support includes breathable air, water, food, waste processing, and medical care. Engineering support includes power generation, heat rejection, materials endurance, corrosion resistance, maintenance, and the ability to manufacture spares. Operational support includes communications, navigation, transport between orbits and the atmosphere, logistics planning, and rescue protocols. Social support includes governance, training, and law. Each criterion has measurable thresholds, and failure in any one criterion can end the project. Self-sufficiency is treated as a multi-loop system. Air must be produced and kept at safe partial pressures. Carbon dioxide must be removed and recycled. Water must be captured, purified, and recovered from waste streams with high efficiency. Food production must be predictable in mass, nutrients, and timing, or it must be replaced by stable long-term storage with controlled rotation. Structural materials must resist the external environment and the internal atmosphere of habitats. Tools and machines require a supply of parts and the methods to repair them. Energy systems must match demand under expected and unexpected loads. Waste must be converted to harmless forms or useful inputs. The loops must remain stable without continuous shipments from Earth, because interplanetary supply lines are slow and fragile. Timescales are made explicit. Hardware life should be counted in many years, not months. Replacement cycles for critical systems must be planned across decades. Training pipelines for operators and engineers must outlast initial crews. Scientific uncertainty must be reduced to levels that allow risk models to remain valid over long periods. The possibility of stepwise expansion is considered, but every step must be safe on its own. If a step requires emergency support from Earth within days, it is not appropriate for relocation. The data foundation of the analysis is stated. Knowledge of Venus comes from ground-based observations, spacecraft in orbit, atmospheric probes, and landers. Measurements describe global circulation, cloud layers, composition, pressure, and temperature profiles. Surface data are sparse and uneven in coverage. The chemical microphysics of clouds and aerosol droplets is still uncertain in details that matter for material selection. The geological history is interpreted from radar mapping and gravity data, with gaps that affect assumptions about resources and hazards. Because of these gaps, conservative margins are used for design targets and failure thresholds. Uncertainty is managed rather than ignored. Each critical parameter is expressed as a range and paired with an operational margin. If a habitat survives only at the optimistic end of the range, it is considered inadequate. If a material resists corrosion only under laboratory conditions that differ from the cloud chemistry, it is not accepted. If a power system meets demand only during the best illumination and wind, it is not reliable. Uncertainties that cannot be reduced with near-term research are treated as blockers for relocation scale decisions. Comparative context helps interpret the findings. Near-Earth orbit offers rapid evacuation, low communication delay, and abundant sunlight, but limited raw materials. The Moon offers proximity and stable vacuum conditions with well-known hazards. Mars offers lower gravity, lower pressure, colder temperatures, and accessible water ice in some regions, with long communication delays. Asteroid resources offer metals and volatiles with microgravity challenges but no atmospheric corrosion. Against these options, Venus presents a dense, hot atmosphere near the surface, acidic clouds at height, and a slow rotation that affects energy balance. The comparison does not imply preference, but it shows relative difficulty and the scale of countermeasures required. Risk is quantified to guide decisions. Each subsystem has modes of failure, probable rates, detection methods, and mitigations. Single-point failures that cannot be eliminated are identified and isolated with barriers. The severity of outcomes is measured by loss of life, loss of habitat, and loss of mission. Evacuation timelines are compared with failure progression times. If an unrecoverable failure can develop faster than an evacuation can occur, the design is rejected. Inventory buffers, redundancy, and graceful degradation are preferred over complex active controls that depend on perfect sensors in harsh conditions. Goals are clarified to prevent scope drift. Scientific return includes atmospheric chemistry, planetary evolution, and technology validation. Technological goals include high-temperature electronics, acid-resistant materials, and autonomous maintenance. Economic goals, if proposed, must be tied to real markets and not to speculative exports with no buyers. Demographic goals must consider health, education, and legal status for residents born or raised off Earth. Ethical and legal constraints include planetary protection, environmental impact on Venus, and compliance with international space law. Any proposal for large-scale intervention in the atmosphere or orbit is screened against these constraints before engineering work begins. Scaling assumptions are stated early. A population count that remains small can be supplied with specialized parts and food at high cost. A population that grows into the thousands requires industrial processes on site and stable power at the scale of many megawatts. Growth beyond that level requires a complete industrial base, including mining, refining, fabrication, and construction, or a strong and permanent supply fleet. Because Venus presents environmental barriers at every stage of scaling, the threshold for industrial independence is far higher than in low Earth orbit or on the Moon. This difference drives the conclusion that relocation is not feasible in the current or near-future technology frame. Verification and validation methods are set in sequence. Ground tests simulate temperature, pressure, and acid chemistry. Long-duration chambers demonstrate corrosion rates and seal performance. Flight tests in Earth's stratosphere evaluate aerostat materials and automated maintenance. Robotic precursor missions to Venus collect missing data on microphysics, winds, and resource availability. Only after these steps are passed can human operations be considered for short durations. Even then, the gap between safe short missions and permanent settlement remains large. For clarity of language, terms used in the video keep consistent meanings. Habitat refers to a pressurized, human-rated module or cluster of modules. Aerostat refers to a buoyant platform in the upper atmosphere that carries habitats, power systems, and equipment. Surface asset refers to a lander or rover designed for very high temperature and pressure. In situ resource utilization refers to production of water, oxygen, fuels, or materials from local sources. Mass relocation refers to sustained multi-generational settlement with minimal resupply. This framing part establishes a strict standard. The planet is approached as it is measured, not as it is wished to be. The burden of proof is placed on reliability over long durations. The outcome of the later parts will follow from these definitions. The next part presents the basic parameters of Venus that set the initial conditions for any design. The basic physical parameters of Venus set the boundary conditions for any design and determine the scale of all countermeasures. The planet is slightly smaller than Earth, with a radius of about 95% of Earth's and a mass a little over 80% of Earth's. Surface gravity is close to terrestrial values and remains near 9/10 of Earth gravity, so weight, fluid behavior inside habitats, and human biomechanics would not gain the relief that low-gravity worlds provide. The bulk density is similar to Earth's, which points to a rocky body with an iron-rich core, a silicate mantle, and a basaltic crust. These properties make the planet familiar in composition but not in environment. The orbit is nearly circular at about 72% of Earth's distance from the Sun. The orbital period is about 225 Earth days, and the synodic cycle relative to Earth sets launch and transfer windows on a predictable cadence. The closer orbit increases the top of atmosphere solar flux to roughly double the terrestrial value. This high input suggests abundant solar power, yet the cloud system changes the result, and the effective light level at and below the clouds becomes the limiting factor for photovoltaic systems and for any photosynthetic process. The near-circular orbit also stabilizes seasonal energy input, which reduces seasonal extremes but does not remove the challenges created by the atmosphere and rotation. Planetary rotation is slow and retrograde. The sidereal day is longer than the year, but the solar day, which sets the timing of sunrise and sunset, is about 117 Earth days. This slow cycle affects thermal gradients, weather patterns, and planning for power and heat rejection. Day-night transitions at the cloud tops and within the atmosphere unfold over long intervals. Thermal systems must handle prolonged periods with little change in the angle of the sun. The slow rotation also reduces the Coriolis effect at the surface. But the atmosphere responds differently because it does not rotate with the solid planet in a simple way. Axial tilt is small. Seasons are weak compared with Earth. Insolation varies more by latitude and cloud dynamics than by the time of year. For engineering, this means that large seasonal swings in temperature and illumination are not expected. Instead, long, slowly changing day-night cycles and latitude-dependent patterns define the operating envelope. Planning for power generation, thermal management, and communication windows must account for these long cycles rather than for sharp seasonal contrasts. The planetary albedo is high because of a global cloud deck. A large fraction of sunlight is reflected back to space before it can heat the lower atmosphere and the surface. Despite the high incoming flux at the top of the atmosphere, the net absorbed sunlight is limited. The energy balance is then dominated by infrared trapping by the dense carbon dioxide atmosphere. The lower atmosphere becomes a near isothermal high-pressure region where heat is retained efficiently. This balance explains the extreme surface temperature and the small diurnal variation at the surface. For design work, the implication is that surface operations experience persistent heat, while the upper atmosphere offers cooler conditions that vary with height. The atmosphere does not rotate with the solid surface. A super-rotating circulation carries the cloud deck around the planet in a few Earth days. Wind speeds at the cloud level can reach values that move air masses around the globe much faster than the ground below them turns. This circulation creates strong shear with height, wave structures, and large-scale patterns that repeat on multi-day periods rather than on the long solar day. Communications links, balloon navigation, and station keeping in the upper atmosphere must be planned around this persistent flow. The superrotation also mixes aerosols and chemical species, which affects corrosion rates and filter loading for any exposed system. The vertical structure of the atmosphere defines zones with very different properties. Near the surface, pressure is tens of megapascals, and temperature is in the hundreds of degrees Celsius. With increasing altitude, pressure and temperature drop along a lapse rate determined by carbon dioxide and trace gases. At heights around 50 to 60 kilometers, temperature and pressure approach values that are compatible with human habitats from a purely thermodynamic standpoint. Above that, the air becomes colder and thinner, with fewer acid droplets but higher wind speeds and more ultraviolet radiation. Each altitude zone sets a distinct set of requirements for materials, power, and life support. The sharp differences with height make platform choice a primary strategic decision. Cloud composition determines optical properties and corrosion risk. The clouds are made of concentrated sulfuric acid aerosols and are arranged in multiple layers with varying droplet sizes and concentrations. The optical depth is high, so visible light is scattered strongly, and direct sunlight is reduced even when the sun stands high in the sky. Diffuse light dominates under the clouds, which lowers the peak power available to traditional solar panels and complicates agricultural lighting. The presence of acid droplets means that any exposed surface requires chemical resistance and regular maintenance. Filtration and protective coatings become base requirements rather than optional margins. The radiation environment differs from airless bodies. The thick atmosphere shields against many charged particles, so cosmic ray and solar particle doses at cloud level and below are less severe than on the Moon or Mars. However, ultraviolet radiation above the clouds is intense, and electrical activity within the cloud layers, including lightning and transient luminous events, introduces electrical hazards to exposed systems. This mixed environment shifts the design emphasis from heavy radiation shielding to chemical protection, weather tolerance, and lightning mitigation for high-altitude platforms and communications infrastructure. Gravitational and topographic fields affect navigation and mapping. The near-Earth surface gravity simplifies human health planning relative to low-gravity destinations, but it increases the energy cost of ascent from the atmosphere to orbit. Radar mapping reveals broad volcanic plains, highland regions, and impact structures that shape local circulation and wave patterns in the atmosphere. Orographic effects are weaker than on Earth because of the slow rotation and the thick air, but standing waves and lee structures still form and influence balloon trajectories and station-keeping loads. Accurate gravity and wind models are necessary inputs for guidance, navigation, and control. Thermal emission from the planet peaks in the infrared and escapes through atmospheric windows. These windows define how surface and lower atmosphere heat can be radiated to space and how remote sensing instruments operate. For habitats and vehicles, thermal control systems must match the available radiative pathways at their chosen altitude. On the surface, radiators face a hot, opaque environment and become ineffective without active cooling and high-temperature working fluids. In the upper atmosphere, radiators can reject heat to space more efficiently, but coatings and fin structures must resist acid attack and particulate fouling. The electromagnetic environment includes a weak induced magnetosphere shaped by the solar wind rather than a strong intrinsic field. Plasma interactions at the planetary boundary influence radio propagation, especially at low frequencies. Communications across the atmosphere must account for scattering by clouds, refraction by density gradients, and attenuation by aerosols. Line of sight links to orbit require geometry that maintains clearance above the horizon through thick cloud decks. Relay constellations in orbit and at high altitude reduce outage risk and allow lower power at terminals, but they add mass and complexity to the system. Day-night circulation at altitude sets predictable cycles for temperature, winds, and turbulence. Long nights and long days provide extended periods of quasi-steady conditions, followed by slow transitions, unlike the rapid diurnal cycles on Earth. Balloon-borne platforms experience repeated alternations in buoyancy if lift gas temperature tracks ambient light. Control systems must compensate with ballast management, variable volume cells, or active heating and cooling. The slow pace of change helps planning but demands high reliability, because the chance to recover from control errors may come only after long intervals. These parameters together define a narrow operating envelope for any human system. The planet is Earth-like in size and gravity, but not in climate or rotation. Energy is abundant at the top of the atmosphere, but limited under the clouds. The cloud deck reflects sunlight, blocks direct power, and corrodes exposed materials. The atmosphere offers a band of altitude with tolerable temperature and pressure, but the same band carries high winds, electrical activity, and persistent acid aerosols. The slow rotation removes fast daily cycles but imposes long-duration thermal and power regimes. Without a strong intrinsic magnetic field, space weather shapes the plasma boundary and affects high-altitude operations. Any concept that ignores these base conditions shifts risk to later stages where corrections become costly or impossible. From these fundamentals, the next analysis moves to the atmosphere in detail because composition, pressure, and temperature profiles convert general constraints into specific engineering limits for habitats, materials, and power systems. The atmosphere of Venus defines the most restrictive boundary for any human presence. Its bulk composition is almost pure carbon dioxide with a small share of nitrogen and trace sulfur compounds. Water vapor is scarce by terrestrial standards and appears only in parts per million. Oxygen is effectively absent outside equipment. The high molecular weight and the depth of the gaseous envelope create very high pressure near the surface and a strong greenhouse effect that traps heat. The result is a hot, dense, chemically aggressive medium that reaches every exposed system and penetrates every weak seal. Near the surface, pressure is close to 100 times the sea level pressure on Earth, and temperature remains in the range where common metals soften and many lubricants fail. Carbon dioxide at these conditions behaves as a heavy, heat-holding fluid with high density. Convection and conduction transfer heat efficiently into hardware that is cooler than the surroundings. The small diurnal variation at the ground prevents natural cooling cycles. Any device with internal temperatures lower than the environment becomes a heat sink rather than a heat source, and will rapidly absorb heat unless active rejection is provided. Air intakes for cooling or ventilation are not practical in this layer for human systems. With altitude, pressure, and temperature decrease along a gradient set by carbon dioxide thermodynamics. In the band around 50 to 60 kilometers, temperature and pressure fall into a range compatible with human habitats from a purely thermodynamic view. This is the so-called temperate zone. It is not a safe zone. The air remains carbon dioxide with acid aerosols and wind speeds are high. The partial pressure of oxygen is zero without equipment. Protective shells, filtration, and internal environmental control are still mandatory. Above this band, the air becomes colder and thinner, and below it, the environment trends back toward the extreme surface values. The cloud system is continuous on a global scale and is made of sulfuric acid aerosols suspended in carbon dioxide. The acid forms when sulfur dioxide and water vapor are processed by sunlight in the upper atmosphere and combined into droplets that settle into layered decks. 3 cloud layers can be identified by altitude and particle size, with a diffuse haze above. The optical depth of the stack is large. Most direct sunlight is scattered or reflected before it reaches the deeper layers. Diffuse skylight dominates illumination under the main deck. The same droplets that scatter light also coat and corrode any exposed surface. Droplet sizes and concentrations vary with height and time, which changes both optical properties and corrosion rates. Chemical aggression is a central hazard. Concentrated sulfuric acid attacks many metals and most common polymers. Protective choices are limited to specific fluoropolymers, selected glasses, noble metals, and certain ceramics, each with its own mechanical limits. Coatings that resist acid often lose adhesion under thermal cycling or crack under flexing. Seals and gaskets must keep integrity while exposed to both acid and ultraviolet light. Filters clog as droplets collect and dry into deposits. Any moving part encounters both chemical and mechanical wear. Maintenance intervals become short unless error-tolerant designs, redundant paths, and easy replacement procedures are built in from the start. Atmospheric dynamics complicate platform stability and navigation. The cloud deck and the layer just below it are carried around the planet by superrotation. At cloud top, air masses circle Venus in a few Earth days. Typical horizontal wind speeds at operational altitudes for aerostats reach values that impose continuous aerodynamic loads on hulls, tethers, and appendages. Vertical motions are weaker on average but include gravity wave oscillations and shear layers that can stress structures and change lift. Station keeping must be done by riding with the flow and by managing altitude to select layers with suitable winds. Precise hovering over one ground point is not realistic for long durations. Electrical activity is present within the cloud system. Lightning and related transient events create electromagnetic pulses and local charge separation. Acid droplets act as electrolytes and can support leakage currents across insulators and coatings, especially when surfaces are wet. High voltage power systems and long conductors must be designed to avoid corona, arcing, and uncontrolled discharge. Bonding and grounding strategies require materials that keep low resistance paths even after long exposure to acid and ultraviolet light. Transient protection on signal lines and radio equipment must tolerate repeated surges without maintenance access for extended periods. The radiation environment below the cloud tops is moderate for human equipment compared with airless bodies. The thick carbon dioxide layer provides shielding against many energetic particles. Ultraviolet radiation, however, is strong at and above the cloud tops and degrades polymers, paints, and coatings. Within the clouds, scattered UV still reaches surfaces and works together with acid to break down materials. Design choices must consider both chemical and photonic damage. Optical windows and solar arrays need protective layers that resist both etching by acid and embrittlement by UV. Illumination under the cloud deck is diffuse and variable. Direct solar input is low even when the sun is high because the cloud stack scatters light. The spectral distribution shifts toward wavelengths that pass more easily through the aerosol layers. Photovoltaic systems operate at reduced efficiency unless paired with concentrators or positioned above the densest cloud layers. Agricultural lighting inside habitats cannot rely on ambient light and must be supplied by electrical systems. This increases baseload power and heat rejection demands and couples food production to power system reliability. Toxicology and human safety rules remain strict at all altitudes. Carbon dioxide at any significant partial pressure is not breathable and can cause hypercapnia if leaked into a habitat. Sulfuric acid aerosols irritate and damage skin, eyes, and respiratory tissue on contact. Protective suits for external work must keep positive pressure and isolate the wearer from both gas and liquid phases. External joints and visors need abrasion and acid resistance. Airlocks must include washdown and neutralization stages to prevent carry-in of acid to the interior. Filters and neutralizers become consumables that must be tracked, replaced, and regenerated within a closed logistics loop. Heat transfer has direct effects on power and life support. In the temperate band, convective cooling to ambient air is possible but is limited by the properties of carbon dioxide and by acid deposition on radiator fins. Radiators exposed to the sky must shed heat through atmospheric windows while resisting fouling by droplets. In the layers near the surface, radiators become inefficient because surrounding gas is hot and radiative escape to space is blocked by the overlying atmosphere. Internal heat must then be stored, pumped to higher altitudes, or rejected by expendable mass, which is not compatible with long missions or settlement scales. In situ resource use faces chemical and physical limits imposed by the atmosphere. Water is present only in trace amounts, so any plan that depends on harvesting significant water from ambient air must move very large volumes of gas or import hydrogen and combine it chemically with carbon dioxide. Sulfuric acid can be neutralized to make sulfate salts, but this process consumes base materials that must also be supplied. Oxygen can be produced by splitting carbon dioxide or by electrolysis of water if water is available, but both paths are energy intensive and require catalysts and membranes that withstand acid and carbon dioxide without rapid degradation. Fouling by aerosols and trace contaminants lowers efficiency and increases maintenance. Radio propagation through the atmosphere is affected by scattering, absorption, and refraction. Thick cloud layers attenuate some frequencies and introduce multipath effects that cause fading. Stable links to orbit require geometry that clears the horizon through dense clouds and uses bands that suffer less attenuation. Redundancy through multi-hop relays and diversity in frequency and polarization reduces outages but increases system complexity. Antennas and radomes must remain transparent to chosen bands while resisting acid and ultraviolet exposure. Uncertainties remain in microphysical parameters that matter for long-duration designs. Droplet-size distributions, concentration profiles, and chemical composition vary with altitude, latitude, and time. The presence and role of unknown ultraviolet absorbers in the clouds introduce additional variance in radiative transfer and heating. Long-time series at the required resolution are limited. Conservative margins must be applied to coating lifetimes, filter loading, window fouling, and solar power output. Designs that depend on tight predictions of these variables without buffers are not credible for settlement scale. These atmospheric facts constrain every later choice. Platform altitude selects pressure, temperature, wind load, corrosion rate, and light level. Material sets are narrowed to a small group that can survive acid and UV while meeting structural needs. Power systems must close a difficult balance between low solar input under clouds and high loads from lighting and environmental control. Logistics models must include a continuous stream of replacement parts and chemicals for neutralization and filtration. With these constraints in view, the analysis of the surface and geology explains why direct ground operations add further limits rather than relief. The surface of Venus is a hot, dense, chemically reactive environment that defines the hardest boundary for any plan beyond brief robotic visits. Knowledge comes from radar mapping, gravity measurements, and a small set of landers that operated only for short periods. The global picture shows broad volcanic plains interrupted by deformed highlands and volcanic constructs. The crust appears basaltic. Mechanical and thermal conditions dominate every engineering choice and reduce margins for error to very narrow ranges. Most of the lowlands are smooth volcanic sheets formed by extensive lava outpourings. Flow fields connect into channel systems that run for hundreds of kilometers and sometimes longer, indicating low viscosity lavas and sustained eruption rates in the past. Surface roughness at the scale of vehicles includes fractured crusts, blocky ejecta around craters, and consolidated regolith. Bearing strength for landers is not uniform and must be treated as variable from site to site. Anchoring, leveling, and traction systems face a dense atmosphere that loads every exposed surface, while the hot ground conducts heat into structures. Wheels, tracks, and legs must test against creep in materials at high temperature and against softened lubricants. High-standing regions include plateau-like terrains with complex deformation patterns. These areas, often referred to as heavily tectonized blocks, show intersecting ridges and folds that record a long history of compression and shear. Their age relative to surrounding plains suggests that they are among the oldest preserved surfaces. The rock fabric is likely stronger and more fractured than in the plains, which complicates drilling and anchoring. Slopes are steeper, and radar bright signatures imply differences in texture, composition, or surface cleanliness. Any site selection process must account for mechanical stability, local relief, and the risk of rockfall or surface sliding under thermal cycling. Volcanic features are abundant. Large shield volcanoes rise above surrounding plains and show radial flows and collapsed structures. Dome-shaped edifices, including pancake-like forms, indicate viscous lavas that built thick, steep-sided units. Radial and concentric fracture systems around volcanic centers form corridors of weakened rock that could become paths for gas release or future collapse. Corona-like structures, where circular or oval deformational patterns surround a central zone, point to mantle upwelling or sagging of the crust over buoyant material. These patterns suggest that internal heat still moves through the lithosphere in focused regions rather than through globally distributed plate motion. Impact craters are fewer than on airless bodies because the atmosphere filters smaller projectiles. The surviving craters are relatively large and spread widely across the surface without the strong age clustering seen on heavily cratered worlds. This distribution is compatible with a surface that was resurfaced on large scales in the geologic past. The exact timing, duration, and mechanism of resurfacing remain uncertain. Episodic overturn of large areas and gradual infilling by plains lavas are both considered. For engineering, the practical consequence is that near-surface rock is largely volcanic. Mechanical properties vary with flow type and cooling history, and inherited structures may be buried or exposed unpredictably. The absence of active plate tectonics sets the mode of heat loss. Without mobile plates, the lithosphere likely thickens and relaxes heat by conduction, plume-fed volcanism, and regional deformation. Rifts and lineaments mark areas of extension where the crust has been pulled apart. Compressional belts mark zones of shortening with stacked ridges. These stress regimes affect fracture networks, permeability, and the stability of excavations or subsurface structures. They also influence the regional distribution of potential resources such as iron-rich basalts or sulfur-bearing deposits. Any plan that assumes predictable, laterally continuous layers over large areas is not well supported by observations. Thermal and pressure conditions at the ground are extreme by terrestrial standards. The ambient temperature is high enough to limit the strength of common alloys, accelerate creep in structural metals, and degrade many coatings. The pressure of the overlying atmosphere makes the gas dense and efficient at heat transfer. Surfaces cooler than the air absorb heat by convection and conduction. Radiators that rely on a temperature drop to the environment lose effectiveness. Internally cooled compartments must move heat to higher, cooler layers to achieve net rejection, or they must store heat and survive on thermal inertia for limited durations. Both strategies conflict with continuous human presence and heavy-duty industrial activity. The chemical environment at the surface is dominated by carbon dioxide with minor reactive gases. Acid droplets formed higher up do not reach the ground in liquid form because they decompose or evaporate before descending through the hot layers. Corrosion at the surface is therefore driven less by liquid acid and more by high-temperature reactions with carbon dioxide and sulfur-bearing gases, along with oxidation and carburization processes in exposed alloys. Ceramics, refractory metals, and stable coatings extend lifetimes but do not remove the need for periodic replacement. Optical components for cameras and instruments require windows that resist chemical attack and remain transparent at elevated temperature. Dust and fine particles can sinter or adhere to hot surfaces and reduce optical throughput. Lighting and visibility are constrained by the global cloud cover above. Illumination at the ground is dim and strongly scattered. The spectral distribution is shifted by the atmosphere, which affects sensor selection and calibration. Imaging through small atmospheric windows in the near-infrared allows limited observation of the lower atmosphere and the surface from above. But on the ground, cameras must balance low light levels against high sensor temperature and the risk of contamination. Active illumination increases power and heat loads and accelerates material degradation. Navigation by vision alone is unreliable over long distances, and radar or LiDAR must operate through hot, dense gas that produces attenuation and backscatter. Mobility systems on the ground face a coupled set of mechanical and thermal constraints. Bearings, gears, and seals must work in a regime where many conventional lubricants break down and where polymeric components lose strength. Dry lubricants and solid bearing materials offer partial solutions, but add friction losses and heat. Motors and actuators must produce torque without exceeding internal temperature limits. Cable insulation, connectors, and harnesses need materials that do not outgaze or crack under sustained heat. Every moving system becomes a source of additional heat that must be rejected in an environment that resists heat flow away from the vehicle. Slow, deliberate movement with minimal articulation extends lifetime but limits area coverage. Drilling, coring, and sampling are technical challenges with few margins. Tools must cut or abrade rock at temperatures where steel soften and where carbide and ceramic elements face thermal shock during contact and withdrawal. Cuttings management is complicated by dense gas that does not clear debris as efficiently as air at Earth conditions, and by the absence of liquid coolants that would boil or decompose. Sample transfer into instruments requires pressure seals and feed mechanisms that function without elastomeric gaskets. Analytical instruments need sensors and electronics that remain accurate at high temperature and can be calibrated in place. Each operation must complete quickly before tool wear or thermal drift exceeds limits. Long-lived static installations on the ground must consider foundation design under thermal expansion and potential creep of the substrate. Structures expand and contract slowly as internal temperatures change, and differential expansion between materials induces stress at joints and fasteners. The substrate itself can change mechanical properties with temperature and time. If loads are carried through pads or piles, contact pressures and thermal gradients combine to change settlement behavior. Designs that use compliant interfaces and allow for controlled movement reduce stress concentrations, but complicate precision alignment of antennas or instruments. Seismic knowledge is limited. Without a network of seismometers, only indirect inferences can be made about quakes and internal activity. Thermal tides and atmospheric loading can excite surface motions at small amplitudes. Volcanic areas may experience local flexure or subtle uplift and subsidence. Conservative planning treats the environment as one where low-level vibrations and occasional shocks are possible. Equipment that depends on fine alignment or long unsupported spans requires bracing or isolation that remains effective at high temperature and does not rely on elastomers. Communications from the surface to orbit must pass through a thick, inhomogeneous atmosphere. Refraction bends paths near the horizon. Scattering by aerosols and absorption at specific bands reduce link margins. Antennas heat under solar and thermal load, and radomes must keep radio transparency while resisting chemical change. Pointing and tracking systems need accuracy that is hard to maintain when structural elements creep and when actuators must move slowly to avoid overheating. Relays at altitude improve coverage and reduce required ground power, but add dependencies on platforms exposed to different hazards. Evidence for recent volcanic or thermal activity on Venus has been reported from orbital data, but the spatial and temporal patterns remain uncertain. For settlement planning, such activity is treated as a localized hazard that can change gas composition and ground stability near active centers. Site selection avoids regions with fresh-looking flows, thermal anomalies, or strong deformation patterns unless the mission is explicitly designed to study them. Even far from activity, gases released higher in the column will be mixed by circulation and can change corrosion rates over time. From the standpoint of human presence, these surface realities convert into operational limits. Hardware lifetimes are short without aggressive thermal management and specialized materials. Power generation at the ground is constrained by low light, high temperature, and corrosive chemistry. Maintenance requires frequent intervention by machines designed to work where people cannot safely operate outside pressurized, high-temperature rated enclosures. Logistics chains that would bring spares and tools must handle descent and ascent through a deep atmosphere and deliver items that survive ground conditions without rapid degradation. When these factors are compared with the relatively milder constraints at higher altitudes, the conclusion follows that long-duration activity on the ground does not offer a stable base for settlement. The surface and its geology therefore define more of a boundary condition than a destination. It is a place where probes and specialized instruments can function for limited periods to answer targeted questions. It is not a platform for continuous human industry or habitation. The next analysis moves to materials and electronics, because the endurance of components in this environment determines whether any platform, surface or airborne, can operate long enough to support even a small, resupplied outpost, let alone a self-sustaining community. Materials and electronics determine whether any platform on or above Venus can operate beyond a short trial. The environment forces selections toward a narrow set of substances and device types. Each selection must be justified by heat tolerance, chemical resistance, mechanical stability, and the ability to keep performance over long intervals without frequent service. The result is a design space that prefers metals with high softening points, ceramics with stable lattices, and polymers with strong carbon-fluorine bonds. Electronics must either operate at elevated temperature with reduced performance or remain inside insulated, cooled volumes that add mass and complexity. Metals serve as primary load-bearing elements and as barriers against gas and liquid. At the surface, common structural steels lose strength and creep at temperatures that approach their design limits. Nickel-based superalloys maintain strength longer, but still face grain growth and oxidation in carbon dioxide-rich gas. Titanium alloys form stable oxide layers at moderate temperature, but these layers can grow and spall under thermal cycling, and strength drops as temperature rises. Tantalum and niobium resist many acids but oxidize at high temperature unless protected. For airborne platforms at 50 to 60 kilometers, temperatures are lower, so corrosion rather than creep becomes the main limit. In that band, stainless steels with molybdenum, Hastelloy-type alloys and titanium alloys gain more practical value because load cycles are manageable and protective films remain intact longer. Alloys with copper and zinc are avoided because acid aerosols can drive rapid dezinsification and pitting. Ceramics and glass ceramics provide hardness, oxidation resistance, and low creep. Silicon carbide and alumina remain stable at surface-level temperatures and are candidates for hot structures, thermal liners, radiator fins, and bearings without oil. Silicon nitride offers high strength at temperature for rolling elements. Zirconia-based ceramics tolerate thermal shock if stabilized correctly. On the surface, alumina and silica can react in strong acids at high temperature, so exposure to liquid acid is avoided by placing ceramic parts behind shields or by using dense glazed surfaces. In the cloud layer, where temperature is lower but concentrated sulfuric acid is present, glazes and dense sintered faces reduce penetration and grain boundary attack. CVD diamond films and sapphire windows provide optical access with high chemical resistance and hardness when other glasses etch too quickly. Each ceramic component requires a joint design that avoids brittle fracture under differential thermal expansion against metals. Polymers are selected only when fluorination or aromatic stability provides margins. PTFE, PFA, FEP, and ETFE resist concentrated sulfuric acid and provide low surface energy that sheds droplets. They creep under load and lose strength at elevated temperature, so they serve as coatings, cable jackets, and soft liners rather than primary structures. PEEK and PPS perform well in many chemicals, but concentrated oxidizing acids and ultraviolet exposure shorten life. Service in the cloud deck requires UV shields or metallic braids. Standard epoxies and polyesters degrade quickly and are not used for exterior bonds. Adhesive joints that must endure outdoors are replaced by brazing, welding, riveted joints, or mechanical clamps with fluoropolymer gaskets that can be inspected and replaced. Inside pressurized habitats, conventional engineering polymers are acceptable because the internal atmosphere is controlled and filtered. Coatings extend the life of metals and polymers by providing chemical barriers and cleanable surfaces. Fluoropolymer topcoats reduce wetting by acid droplets and allow washdown. Dense metallic plating such as gold, platinum, or tantalum reduce corrosion at edges and fastener heads but require careful control of porosity and underlayer selection to avoid galvanic couples. Ceramic coatings applied by physical vapor deposition or atomic layer deposition create thin, conformal barriers on complex shapes, but pinholes and microcracks must be managed with multi-layer stacks and inspection. In the cloud layer, ultraviolet light and charged particles add photodegradation to chemical attack. UV-absorbing overcoats and sacrificial films create a planned maintenance cycle where outer layers are stripped and renewed at set intervals. Seals, gaskets, and feed-throughs are critical points. Elastomers lose properties under hot acid and ultraviolet exposure, so they are avoided for exterior dynamic seals. Metal C-rings, spring-energized PTFE seals, and knife-edge flanges create reliable static joints. Glass-to-metal and ceramic-to-metal feed-throughs provide hermetic electrical and fluid interfaces. Alloys with matched thermal expansion such as Kovar protect against crack formation. Where motion is unavoidable, bellows and magnetic couplings move work across a pressure boundary without sliding seals. Airlocks on aerostats include rinse and neutralization stages. Internal drains collect wash liquids for regeneration. The design goal is to minimize seal count, maximize accessibility, and keep each seal in an environment with stable temperature and low UV. Bearings, gears, and sliding interfaces use dry film and solid lubricant systems. Molybdenum disulfide performs poorly in strong oxidizers, so it is not relied upon in exposed areas. Alternatives include graphite, hexagonal boron nitride, chromium nitride coatings, and ceramic rolling elements. Greases and oils remain inside sealed compartments with controlled atmospheres, and thermal management keeps them below their breakdown temperatures. Flexural pivots replace sliding joints in mechanisms that cycle frequently with small motions. Where high torque is needed, sealed gearboxes exchange heat through corrosion-resistant walls with internal oil circuits and external radiators protected by louvers and hydrophobic meshes that reduce droplet deposition. Cabling and connectors must carry power and data while resisting acid, UV, and mechanical wear. Conductors use tinned or nickel-plated copper to limit corrosion under pinholes. Insulation uses PTFE, PFA, or ETFE with metallic braids that act as both abrasion shields and Faraday cages. Connectors are hermetic or use double O-rings placed in protected volumes. Latch mechanisms are large enough for glove service and designed to shed liquid. For exposed antennas and sensors, RF windows use PTFE-based laminates or ceramic radomes with hydrophobic treatment. Strain reliefs avoid sharp bends that concentrate stress in softened polymers after long exposure. Thermal protection is platform-specific. On the surface, passive insulation cannot stop heat soak for long because convective and conductive transfer from hot dense gas overwhelms multi-layer blankets. Hot structures with internal coolant loops extend operating time, but they require pumps, high-temperature fluids, and robust power. On aerostats, convective flux is lower, and multi-layer insulation combined with reflective foils behind acid-resistant skins reduces heat gain. Radiators face the trade between surface area and fouling. Fin spacing and surface energy are tuned to let droplets detach under vibration and wind. In both regimes, coatings with low emissivity at solar wavelengths and high emissivity in infrared windows improve balances, but deposits shift properties over time and must be cleaned or accepted as a life limiter. Electronics define the boundary between human-scale operations and short-lived demonstrations. At the surface, ambient temperatures exceed the limits of standard silicon. High-temperature silicon on insulator devices operate to about 200 to 300 degrees Celsius with derated speed and lifetime. This is insufficient for continuous work at Venus ground conditions. Wide bandgap semiconductors such as silicon carbide and gallium nitride function at higher temperatures. Integrated circuits in silicon carbide can operate above 300 degrees Celsius, with research devices reaching higher, but practical system complexity remains low compared with standard electronics. Packaging uses ceramic substrates, thick film interconnects, and high-temperature solders. Passive components are the bottleneck. Electrolytic capacitors are excluded. Polymer dielectrics age quickly, and only selected ceramic capacitors and wire wound components survive. Where computation and data handling exceed the high-temperature stack, electronics remain in cooled compartments behind thermal barriers, increasing mass and power. In the cloud layer, standard commercial electronics operate if kept dry and protected. Enclosures maintain slight overpressure with clean, dry, inert gas to exclude aerosols. Conformal coatings alone are not relied upon because strong acids and UV find defects. Instead, conformal layers serve as a secondary barrier inside sealed housings. Surge protection is mandatory due to lightning and electrostatic events. Gas discharge tubes, MOVs, and spark gaps are placed across lines inside sealed volumes. Grounding meshes integrate hull, mass, and equipment into a single potential reference. All protective devices are sized for repeated pulses without replacement for long intervals. Sensors and actuators require special packaging. Optical sensors look through windows of sapphire or diamond with scratch-resistant outer films. Windows mount on flanges that allow easy swap without opening main housings. Pressure sensors are isolated from corrosive gas by metallic diaphragms with oil fill on the protected side. The fill fluid is chosen for low vapor pressure and thermal stability. Gas analyzes condition samples through heated lines, coalescers, and filters that remove droplets before gas reaches sensitive elements. Valves and pumps use corrosion-resistant alloys, ceramics, and fluoropolymers. Dead volumes are minimized to reduce areas where acid can pool and concentrate. Power conversion and storage set practical limits on operations. Photovoltaic arrays at cloud level produce less energy than their area suggests because of diffuse light and spectral shifts. Cover materials must be acid-resistant. Fluoropolymer front sheets and sealed edges protect cells at the cost of additional reflection and minor efficiency loss. Power electronics use derated components to improve life. Inductors and transformers use high-temperature cores and enamel with acid-resistant overcoats. Batteries inside habitats remain in controlled atmospheres. Lithium-ion chemistries operate normally if temperatures stay within design range, but acid ingress is unacceptable and triggers conservative enclosure design. At higher temperatures, sodium, sulfur, or thermal batteries can provide burst of power for external tools, but they require strict thermal management and safe handling. Mechanical storage such as flywheels sits inside dry compartments and avoids chemical exposure. Bearings and vacuum housings must be designed for long life with minimal service. Maintenance philosophy drives many material choices. Surfaces that must stay clean receive hydrophobic and oleophobic treatments, so droplets coalesce and detach. Rinsing systems use water and mild alkaline agents to neutralize acid films on critical interfaces. Supplies are metered, reclaimed, and regenerated to close the loop. Fasteners are standardized, oversized, and placed for access by teleoperated tools. Modules use blind mate connectors and guides to limit handling time in exposed conditions. Every external component has an assigned service interval that reflects measured corrosion rates and UV dose. Spares are stored in sealed racks and are unpacked only when needed to reduce cumulative exposure. Local manufacturing on Venus is constrained by feedstock chemistry. Fluoropolymers require fluorine-bearing precursors that are not available in useful concentration. High-performance alloys require multi-element control that is not achievable with unrefined basalts. Ceramics need controlled powders and sintering equipment that would take a heavy industrial base to produce. As a result, replacement parts and coatings for acid and UV exposure come from Earth for the foreseeable future. Only simple metal structures, fasteners, and some glass or ceramic items could be made locally after long investment in precursor missions. This dependence on external supply increases cost and risk and argues against settlement scale. Reliability engineering ties material and electronic limits into system architecture. Designs reduce the number of exposed moving parts, prefer passive stability over active control where possible, and keep critical computation in protected cores. Fault detection relies on simple, robust sensors backed by mid-level diagnostics rather than on complex, high-speed analytics at the point of exposure. Units fail in predictable, inspectable ways, and replacement is faster than repair. Data links and power feeds offer alternate paths. These choices increase mass and may reduce peak performance, but they increase survival time in a medium that degrades everything it touches. These constraints and selection show that even with careful engineering, endurance in Venus conditions demands continual protection, inspection, and replacement. At the surface, only simplified high-temperature electronics and ceramic-heavy mechanisms function for limited periods. In the cloud layer, standard electronics survive inside sealed volumes, but coatings, seals, and exposed hardware require a maintenance pipeline. The next analysis covers energy and in-situ resources, because available power and locally sourced inputs determine whether such protected systems can operate at scale without constant resupply. Energy supply and local resource use set the limits for any activity on or above Venus. Power must be available without long interruptions, and it must be delivered through hardware that survives acid aerosols, ultraviolet light, and mechanical loads from persistent winds. Storage must bridge the difference between variable generation and continuous demand. Resource schemes must start from the actual composition of the atmosphere and from the absence of accessible liquid water. When these requirements are evaluated together, it becomes clear that continuous operation relies on a combination of solar and nuclear sources at altitude, supported by conservative storage, while in situ resource use remains narrow and energy intensive. Solar power appears attractive because the top of the atmosphere receives a higher solar flux than Earth. The cloud deck reduces this advantage. Above the main clouds, direct sunlight is strong and supports efficient photovoltaic arrays with manageable thermal loads. Arrays must be encapsulated in acid-resistant front sheets and sealed at edges to prevent ingress. Mounts and frames require corrosion-resistant alloys and fluoropolymer skins. Below or within the clouds, illumination becomes diffuse and weaker. The spectral distribution shifts and panel output falls. Agricultural lighting and life support cannot rely on ambient light and must draw from electrical systems. A floating platform that lives within or just under the cloud tops can choose mast-mounted arrays that reach into brighter layers, but every square meter adds mass, area, and maintenance. Cleaning is needed because acid droplets and dust reduce transmittance. Rinse systems consume water and bases for neutralization, which ties cleaning to the water loop and to chemical stockpiles. Day-night cycles for platforms at cloud altitude are set by the motion of the air relative to the sun. Because the atmosphere circles the planet in a few Earth days, a buoyant habitat experiences multi-day light-dark periods rather than the 117-day solar cycle of the solid surface. Storage must handle several days of reduced or no production without deep cycling that shortens battery life. If arrays sit above the densest clouds, average production improves and storage needs shrink, but exposure to ultraviolet and charged particles increases and structural loads rise. Designs that keep solar as the sole prime source must oversize both arrays and storage and accept frequent surface maintenance under acid and wind. Wind power is tempting because of the dense atmosphere and strong flows at altitude. Turbines can extract significant power per sweep area at modest wind speeds. The same density that improves power also increases loads on blades, hubs, and towers, and it imposes constant vibration on the platform. Bearings and gearboxes need sealed environments and active cooling. Erosion from acid droplets and suspended particles reduces blade life unless skins are ceramic-filled or metal-sheathed, which adds mass. Crosswind kite systems reduce structural mass, but introduce complex tether dynamics in a corrosive medium with lightning risk. Wind can supplement solar, especially at night, but it rarely replaces it because power fluctuates and maintenance is heavy. A combined solar-wind architecture smooths generation but duplicates exposure to corrosion and mechanical wear. Nuclear sources provide steady power that is decoupled from light and wind. Radioisotope power supplies deliver reliable heat but at low electrical output and are best reserved for instruments and critical keep-alive loads. compact fission reactors can meet multi-megawatt demands for habitats, industry, and ascent vehicle support. Heat rejection defines feasibility. At the surface, ambient temperature and the opaque atmosphere limit radiator effectiveness and force reactors to operate with high coolant temperatures and large radiators that still struggle to shed waste heat. At altitude, radiators can reject heat through atmospheric windows and to space. Panels require acid-resistant skins, droplet-shedding textures, and inspection access. Shielding mass is significant, but it can be arranged to protect crew spaces and sensitive electronics while leaving other directions open. Fuel delivery and end-of-life handling introduce logistics and safety tasks that must be planned with conservative margins and with redundancy in control and shutdown systems. Storage closes the gap between variable generation and continuous load. Inside habitats, lithium-ion batteries operate well if kept dry and within temperature limits. Outside, housings must be sealed and pressure balanced. For multi-day bridging, battery mass grows quickly. Flow batteries offer long cycle life and scalable capacity, but electrolytes require chemistries compatible with closed habitats, and membranes cannot see acid aerosols. Mechanical storage such as flywheels suit short-term smoothing and can sit inside dry compartments. Bearings and vacuum housings become the limiting parts. Hydrogen as an energy carrier helps seasonal or multi-day storage if hydrogen is available. It feeds fuel cells that return electricity and water, but tanks, valves, and membranes must resist acid and ultraviolet in case of leaks or external installation. Thermal storage with phase change salts can shift heat for hours to days and support reactor load following, but it cannot power life support on its own. The atmosphere defines what can be made locally. Carbon dioxide is abundant, nitrogen is present at a useful fraction, sulfur dioxide and sulfuric acid provide sulfur and oxygen, and water exists only in trace amounts. Oxygen for breathing or oxidizer can be produced by solid oxide electrolysis of carbon dioxide. This process runs at high temperature and needs durable ceramics, metallic interconnects, and catalysts that do not poison quickly. It yields oxygen and carbon monoxide. Oxygen is usable directly. Carbon monoxide is a fuel only if paired with an oxidizer that equipment can handle safely. Reverse water-gas shift uses hydrogen to convert carbon dioxide to carbon monoxide and water. If hydrogen is available, the water is captured for the life support loop, and hydrogen can be recovered by electrolysis at the cost of power and electrode maintenance. Both routes demand significant electricity and sustained high temperatures, and both place stress on seals and catalysts in the presence of acid contaminants. Water is the primary constraint for any settlement concept. Ambient air contains very little, and cloud droplets hold water bound in sulfuric acid. Collecting droplets from airflow provides acid that must be neutralized or decomposed. Neutralization with basic minerals consumes reagents that are not available in the atmosphere and would need to be imported or mined and refined on the surface, which defeats the purpose. Thermal decomposition of sulfuric acid yields water and sulfur oxides at high temperatures, but reactors, heat exchangers, and catalysts must survive in a hot, corrosive stream. Any water gained must exceed what is lost to cleaning, leaks, metabolic consumption, and processing inefficiencies. In practice, closed-loop water recovery inside habitats reaches high efficiency and covers most needs, while makeup water comes from imported hydrogen reacted with carbon dioxide. This approach converts a mass of hydrogen into a larger mass of water and oxygen, but it binds the settlement to a supply line and to high electrical loads for electrolysis and compression. Fuels for vehicles and ascent stages require hydrogen or other light elements that are not present in the atmosphere at useful levels. Methane production by Sabatier reaction consumes hydrogen and carbon dioxide and yields methane and water. Methane can serve as fuel for engines or fuel cells, and the water is recycled. Without local hydrogen, methane ISRU reduces to reshuffling imported mass. Carbon monoxide can function as a fuel with oxygen, but delivers lower specific impulse and poses handling hazards. Ammonia would serve as hydrogen carrier and as a base for acid neutralization, but it is not available in the atmosphere, and synthesis demands hydrogen. All fuel cycles that start with atmospheric carbon dioxide and end with storable propellants require large power inputs, corrosion-resistant reactors, and precise thermal control, which increases system count and maintenance. Nitrogen from the atmosphere is useful as a buffer gas for habitats and for industrial processes. Capture requires compression, drying, and separation from carbon dioxide. Cryogenic processes are efficient at scale but add mass and complexity and require reliable heat exchangers and insulation. Pressure swing adsorption is possible but needs sorbents that tolerate trace acid gases without rapid degradation. Once separated, nitrogen is straightforward to store and handle, and it reduces oxygen partial pressure and fire risk inside habitats. Sulfur compounds provide feedstock for sulfuric acid management and for some industrial chemistries, but most processes that consume sulfur also consume bases or hydrogen and do not close inside the local inventory. Power distribution and conversion under acid and ultraviolet exposure add their own limits. Direct current microgrids reduce conversion losses and ease integration of storage and solar arrays. Converters and inverters sit inside sealed compartments with forced air or liquid cooling drawn from clean internal loops. External runs use plated conductors, fluoropolymer insulation, and shielded cable trays with drainage to prevent liquid pooling. Lightning and static discharge protection sits at entry points and grounds to a common reference that ties hulls, masts, and arrays together. Connectors for replaceable modules are large, keyed, and operable by teleoperated tools to reduce time outside. Heat rejection is the partner of every energy system. On the surface, radiators struggle, and convective exchange raises internal temperatures instead of lowering them. Only short operations with internal thermal storage or pumped loops to higher altitudes are possible. In the cloud layer, radiators sized for space operation work if kept clean. Surfaces need textures and coatings that shed droplets under vibration and wind. Louvers and meshes reduce fouling but add points of failure. Periodic washdown restores performance at the cost of water and neutralizer. Thermal buses route heat from dense electronics and from electrolyzers to radiators placed in favorable airflow and view factors. The thermal plan must be established before any generator or industrial unit is committed to a given output. When these elements are assembled into complete architectures, patterns appear. Platforms at cloud altitude that combine solar arrays above the densest layers with a compact fission reactor achieve the most stable supply, with batteries and limited hydrogen storage bridging outages and load steps. Wind turbines add value if maintenance crews and spares are available, but they are not prime movers. Oxygen can be made from carbon dioxide at industrial scale with high electrical input, while water remains tied to imported hydrogen and to high-temperature processing of acid if attempted. Fuels based on hydrogen remain import-limited. Every unit that touches the atmosphere must accept corrosion, fouling, and inspection cycles, and every wash, filter change, and coating renewal ties back to water and chemical inventories. These balances show that energy is available at altitude but never free. Every kilowatt demands mass in arrays, radiators, reactors, storage, and shielding, followed by regular surface work in a medium that degrades materials. Every kilogram of water recovered demands other kilograms of reagents, heat, and maintenance. In situ resource use beyond oxygen from carbon dioxide remains narrow and expensive. With power and inputs defined, the next analysis turns to human life support, because stable internal environments, food, water, and medical care must operate continuously on top of this constrained energy and resource foundation. Human life support on Venus relies on closed, layered systems that keep a stable internal environment while rejecting heat, acids, and contamination from outside. The target cabin atmosphere remains near terrestrial values for pressure, oxygen partial pressure, temperature, and humidity. A typical design maintains total pressure between 70 and 100 kilopascals, oxygen partial pressure near 20 kilopascals, temperature around 20 to 24 degrees Celsius, and relative humidity between 30 and 50%. Nitrogen functions as the primary buffer gas because it reduces fire risk and provides a familiar breathing mix. Nitrogen is separated from the ambient atmosphere in upstream plants and stored in clean tanks to avoid acid carryover. Internal circulation uses redundant blowers, particulate and chemical filtration, and precise sensors that track oxygen, carbon dioxide, carbon monoxide, volatile organics, and trace acids at multiple points. Air revitalization combines fast response and regenerative elements. Carbon dioxide removal employs solid amine beds or pressure swing adsorption with zeolites or metal organic frameworks in multi-column arrangements that keep continuous flow while one column regenerates. Sabatier or Bosch reactors are avoided as primary carbon sinks unless hydrogen is abundant, because water supply and catalyst life become limiting. Oxygen supply comes from electrolysis of recycled water with oxygen storage in high-pressure cylinders for surge demand and emergency reserve. Solid oxide electrolysis of carbon dioxide produces oxygen as a secondary stream in power-rich periods. This route needs high-temperature stacks and careful isolation from cabin air. Passive scrubbing cartridges remain on hand for fires or chemical releases, but routine use depends on regenerable systems to close the mass balance. Moisture control and heat removal are linked. Condensing heat exchangers keep dew point within set limits and recover clean water for the potable loop. Cabin heat loads from people, lighting, cooking, and electronics pass to internal liquid loops that send heat to radiators placed in external housings protected from acid aerosols. These housings maintain clean, dry internal conditions with inert gas purges and hydrophobic meshes at inlets. Radiator surfaces face the sky through optical windows and louvers designed to shed droplets and tolerate ultraviolet exposure. Cooling capacity includes margin for peak metabolic loads during emergency activity and for dehumidification when clothing and equipment bring water into the cabin after external work. Fire safety takes precedence because maintenance activities add ignition sources. Oxygen is held at terrestrial partial pressures, flammable materials are minimized, and cable routes follow segregated trays. Detection includes smoke, heat, and gas sensors in all compartments, with cross-zoned alarms to avoid single-sensor dependence. Suppression inside cabins uses water mist and inert gas floods with nitrogen or argon. Carbon dioxide is avoided in occupied spaces because it increases asphyxiation risk. Compartments that host electrolyzers, batteries, or power converters receive added blast relief and independent vent paths that do not route through living areas. After any suppression, air is scrubbed for particulates and acid gases before the compartment returns to service. Water management closes with high efficiency because external sources are scarce. The potable loop draws from a central tank fed by humidity condensate, urine distillation, and kitchen and hygiene grey water after stage treatment. Pre-treatment uses filters and activated carbon, followed by reverse osmosis and ultraviolet sterilization. Brines and solids from the process move to a waste oxidation unit that converts organics into carbon dioxide and recoverable water. Detergents and personal care products are selected for low persistence and compatibility with membranes and bioreactors. Hygiene infrastructure favors low water fixtures, vacuum-assisted toilets, and controlled time showers. Laundry uses low water cycles with heat pump drying and condensate return. A separate industrial water loop supplies washdown and neutralization fluids for airlocks. Its chemistry is managed to avoid cross-contamination with drinking water. Food supply sets a significant continuous electrical and logistical load. A conservative plan begins with a multi-year stock of shelf-stable foods sized for population and rotation, backed by local fresh production for nutrients and morale. Plant growth units use controlled environment agriculture with LED lighting tuned to crop spectra, recirculating hydroponics or aeroponics, and precise addition of micronutrients. Carbon dioxide generated by crew and equipment feeds the growth chambers after purification. Waste heat from lights is captured by the habitat cooling loop. Calorie-dense staples such as grains and oils remain imported until industrial capacity grows, because growing staples at scale demands large floor area, lighting power, and skilled labor. High-protein supplements can come from algae or microbial fermentation using imported substrates and nitrogen from local separation. Both paths reduce greenhouse area but require food safety controls, downstream processing, and cultural acceptance. Animal husbandry is avoided because feed, water, space, and waste burdens are high. Waste processing prevents accumulation of biological and chemical hazards. Fecal and food waste follow either wet oxidation at elevated temperature and pressure or anaerobic digestion with biogas recovery if the gas can be scrubbed for clean use. The choice depends on power availability and on maintenance capacity. Wet oxidation returns sterile water and concentrated mineral residues that re-enter the nutrient cycle for plants. Digestion provides a slow, steady sink for organics at lower peak power, but demands careful control of microbiology and gas cleanup. Solid residues that cannot re-enter loops are compacted and stored in sealed cassettes for eventual return or disposal in a controlled external container that isolates acids and prevents aerosol formation. Healthcare spans routine, urgent, and long-term needs without rapid evacuation. The medical bay includes basic imaging, laboratory analysis for blood and microbiology, dental equipment, and a small operating room. Pharmacy stocks are managed with cold storage for temperature-sensitive drugs and with on-site compounding for stable generics. Telemedicine links physicians on Earth for consultation with latency that depends on planetary geometry. Protocols assume that definitive care must be available locally for trauma, chemical burns, respiratory injury, and common surgical conditions. Rehabilitation capabilities address fractures and soft tissue injuries under near-terrestrial gravity. Radiation-specific care is not a dominant driver below the clouds, but ultraviolet eye and skin injuries from occasional external work are expected and are prevented by strict visor and skin coverage rules. Human factors engineering stabilizes performance over long durations in a setting with unusual outside cycles. Artificial day-night schedules are maintained with lighting that follows a 24-hour pattern aligned to Earth habit. Dynamic lighting mimics morning and evening transitions and adjusts spectrum to support circadian rhythms. Acoustic design keeps background noise below levels that impair sleep or communication. Equipment that cannot be quieted is isolated in machinery spaces with remote monitoring. Private cabins allow separation and recovery. Shared spaces include greenery to provide humidity buffering, air polishing, and psychological relief. Exercise spaces host aerobic and resistance equipment sized for terrestrial gravity. Schedules enforce daily activity to control cardiovascular and musculoskeletal deconditioning from confinement. Psychological support treats isolation, small group dynamics, and the cognitive load of high-consequence maintenance. Crew selection favors stable, cooperative personalities with cross-training in technical and medical fields. Rotation plans define tour lengths and handover protocols. Communication bandwidth to Earth includes private channels for families and structured social interaction to reduce conflict. Training prepares residents for long nights, diffuse exterior light, and the absence of familiar environmental cues. Monitoring watches sleep duration, mood, and cognitive performance with consent-based protocols and clear privacy boundaries. Interventions include schedule adjustments, lighting changes, counseling, and short duty reassignments rather than pharmacological dependence. External work presents specific hazards that drive suit and airlock design. Suits remain positive pressure with breathable air and active cooling. Outer layers resist sulfuric acid aerosols and ultraviolet light and shed droplets with fluoropolymer skins over abrasion-resistant fabrics. Joints avoid exposed elastomers and use covered bearings or flexures. Visors use coated sapphire or laminated glass with sacrificial outer films. Glove design balances dexterity and chemical protection with multi-layer laminates and frequent replacement. Airlocks incorporate a sequenced washdown of suits with neutralizing fluid, followed by a drying phase and aerosol counting to confirm cleanliness before inner door release. pH sensors and residue monitors log each cycle for quality control. All runoff enters the industrial water loop for neutralization and recovery. Contamination control keeps outside acids and particulates out of living areas and protects sensitive equipment from internal spills. The habitat maintains slightly higher internal pressure than service corridors to drive leaks outward rather than inward. Vestibules and pass-throughs use sticky mats, air showers, and tool covers. Materials inventories track exposure history. Items that have seen external conditions are either decontaminated to a certified level or confined to maintenance zones. Laboratory and food areas maintain stricter air quality classes and independent exhaust. Filters are changed on time or by pressure drop and particle count criteria, with each change treated as a controlled operation to avoid dispersing captured acids and dust. Epidemiology in a closed community remains a constant concern. Quarantine rooms with independent air and waste lines stand ready for isolation. Ventilation zones use pressure cascades that direct flow from clean to less clean areas and then to exhaust. Vaccination schedules and pre-departure screenings reduce import risk. Surface materials inside cabins favor cleanability and antimicrobial performance by physical means rather than by leaching biocides. Monitoring of wastewater provides early signals for outbreaks. If a pathogen emerges, response follows pre-planned cohorting, remote work assignments, and schedule adjustments to protect critical operations. Children and multi-generational presence introduce additional requirements if settlement is claimed as a goal. Prenatal and pediatric care demand expanded medical capability, dedicated living areas, and education programs with safe laboratories and exercise. Nutrition plans adjust for growth. Legal and ethical frameworks define consent, schooling, and healthcare rights in a remote habitat. These needs increase staff counts and space allocations and place steady demands on water, power, and healthcare stocks. Without large, reliable supply and industrial support, multi-generational planning remains speculative. Inventory, spares, and maintenance scheduling run as a parallel life support function. Each consumable has a measured burn rate, safety stock, and reorder point scaled to interplanetary logistics. Spare parts for pumps, valves, sensors, and seals occupy sealed racks with humidity and temperature control. Tooling supports teleoperation and rapid module swaps to minimize time in external suits. Predictive maintenance draws on sensor data for vibration, temperature, and flow to plan interventions before failure. Every maintenance action includes a decontamination budget for water and chemicals, which links work tempo to water production capacity and to neutralizer stock levels. Emergency response closes the loop on credible worst cases. Scenarios include cabin leak, fire in a machinery space, acid intrusion through a failed seal, power loss, and medical emergencies. Each scenario carries a timeline that compares progression to response steps and available resources. Life rafts are not relevant. Instead, safe rooms with independent air, water, and communication provide short-term refuge while faults are isolated and repaired. Evacuation to Earth is not a near-term option within hours or days. Therefore, critical stocks and repair capacity must be sized to bring the habitat back to a safe state without outside help. Drills are scheduled and recorded with the same rigor as reactor tests or airlock cycles. Taken together, these elements define a life support architecture that can sustain a small crew for a limited period with continuous power and steady maintenance. Scaling to hundreds or thousands of residents increases demands on energy, water, and staffing faster than simple linear projections, because every added person adds not only metabolic load, but also maintenance, healthcare, and social infrastructure. The reliance on imported hydrogen for water makeup, the exposure of external hardware to acid aerosols and ultraviolet light, and the requirement for frequent decontamination create high recurring costs and tight coupling between subsystems. These realities set the stage for the next part, which addresses transport, construction, and base architecture, because physical access and platform choice determine how these life support systems are packaged, serviced, and expanded. Transport, construction, and base architecture on Venus are shaped by the dense atmosphere, long day-night cycles at altitude, and the need for continuous service access. The transport chain begins at Earth with assembly and checkout of modules in low Earth orbit. Cargo and crew vehicles depart during efficient windows and follow transfer trajectories to Venus. Capture at Venus is achieved either by propulsive braking into orbit or by aerocapture in the upper atmosphere with a thermal shield and a guidance system that maintains altitude through a narrow corridor. Aerocapture reduces propellant mass but adds heat load and structural stress. After capture, a staging orbit supports checkout, phasing, and coordination with atmospheric platforms. Relay spacecraft in high elliptical orbits provide communications across the limb and reduce outage risk when platforms move under the clouds. Entry, descent, and deployment into the atmosphere use a sequence of thermal protection, aerodynamic braking, and buoyancy. Dense gas allows large drag forces and reduces terminal velocities, but heating during hypersonic entry remains severe. Aeroshells use ablative materials and high-temperature composites that do not degrade in carbon dioxide. After deceleration to supersonic speeds, inflatable decelerators or reefed parachutes increase drag. The chemical environment forces careful choice of fabrics and lines that resist acid and ultraviolet light. At a planned altitude in the temperate band, the vehicle deploys a buoyant envelope and transitions from falling to floating. The envelope fills with a lifting gas that is stored in high-pressure tanks or generated on board from a precursor. The gondola separates from the entry structure, unfolds antennas and radiators, and configures itself for station keeping and power generation. Disposable entry hardware falls away and is not recovered. Ascent from the atmosphere to orbit demands a different sequence. A small rocket launched from near the cloud tops reduces losses in the dense lower layers. The ascent vehicle uses oxygen and fuel carried on board. It rides on a lightweight truss or on a platform attached to the aerostat and is serviced under clean, dry conditions inside a hangar volume that opens to the outside only for launch and recovery. To reduce structural loads at liftoff, the aerostat can hand off the ascent vehicle at a controlled drop and ignite after a short free fall. After orbital insertion, the vehicle docks with a staging spacecraft that stores propellants and returns supplies. Descent vehicles arrive on separate flights and re-enter with their own heat shields and aerosols-resistant parachutes. then transfer to buoyant operation in the same altitude band. Heavy cargo delivery uses the atmosphere as a brake and then transitions to buoyancy with surplus lift that supports slow ferrying to the main base. Cargo modules are designed to survive acid exposure during descent and to connect to gondola frames with blind-mate structural and utility interfaces. Docking fixtures accept minor misalignments and lock with over-center latches that crews can verify by camera. Critical cargo such as reactor components, electrolyzers, and life support cores arrives with double containment and shock isolation to avoid damage during oscillations in the dense gas. Base architecture in the atmosphere centers on buoyant platforms at 50 to 60 kilometers altitude. Each platform consists of a gas cell or a cluster of cells, a structural frame, a gondola with pressurized habitats, and external mass for arrays, antennas, and radars. The gas cell uses an acid-resistant skin and internal baffles that limit slosh and maintain shape. The frame uses corrosion-resistant alloys and composite elements covered by fluoropolymer skins. The gondola is modular. Pressurized volumes house crew quarters, laboratories, medical and food systems, and control rooms. Machinery spaces host power electronics, compressors, pumps, electrolyzers, and thermal buses. Airlocks connect to external decks that are covered, drained, and provided with rinse systems. A segregated hangar supports drones and small service craft. A dry trunk runs the length of the platform and houses cables, pipes, and data backbones in a protected environment with ventilation and fire barriers. Station keeping in the super-rotating flow is achieved by altitude selection rather than by large horizontal thrust. Platforms ride with the wind and adjust height to enter layers with different speeds and directions. Small thrusters handle fine control and relative positioning during docking or maintenance. Predictive navigation uses wind models to plan trajectories and rendezvous times with other platforms. Mooring between platforms is not permanent because relative motion and load cycles would fatigue lines and fittings. Instead, planned meetups occur within corridors where relative speed is minimized and where relay coverage is strong. During meetups, cargo and crew transfer through pressurized docking tubes with isolation valves and quick separation capability. Communications architecture combines line-of-sight radio, atmospheric relays, and orbiting nodes. Antennas sit on masts above the main deck behind acid-resistant radomes. Lightning protection bonds masts, frames, and gondolas into a common ground with low-resistance paths. Surge arresters sit at entry points to sealed electronics bays. Internal networks run as redundant fiber trunks with sealed chemical-resistant connectors. Critical control systems remain on separate hardened networks with limited external exposure. Data from sensors and cameras outside feed through fiber converters to avoid conductive paths across seals. Construction at altitude uses pre-assembled modules and robotic assistance. External cranes, rail trolleys, and teleoperated arms handle heavy components. Workplaces provide tie-off points, non-slip surfaces, and drain channels. Every lift is planned with allowance for gusts and platform motion. Fasteners and guide cones align modules under small relative movements. After placement, technicians inside the pressurized volume engage latches and verify seals with pressure decay tests and chemical sniffers. Rinse and neutralization cycles follow any work that involved opening an external panel. Surface finishes are inspected for damage and patched before returning areas to service. Drones support close visual inspection and small parts delivery to reduce suit time. Power generation hardware sits in zones optimized for airflow and access. Photovoltaic panels occupy masts or outriggers that keep shadowing of radiators low. Wind units, if used, mount on separate booms to limit vibration transmission into the gondola. Radiators face upward and outward and have louver systems that close during acid showers and open during clear periods. Wash lines run to the edges with controlled spray patterns to minimize water use. Tanks for gases and liquids are placed away from crew spaces and separated by firewalls and blast relief panels that vent to the outside. Sensors for leaks monitor hydrogen, oxygen, and hydrocarbons, and alarms tied to automatic isolation valves and power cutoffs. Internal layout separates clean and dirty processes. Living areas, control rooms, medical rooms, and laboratories that handle clean samples are grouped in a clean zone with independent air handling. Workshops, hangars, battery rooms, and airlocks form the service zone. The two zones meet at controlled transfer points with pass-through cabinets and tool sterilization. Food production areas remain near the clean zone to simplify inspection and hygiene, but have their own exhaust and spill containment. The industrial water loop for external washdown remains in the service zone and never connects to potable systems except at controlled recovery units. Docking and logistics follow repeatable procedures. Visiting cargo modules approach along a defined vector upwind of the platform. A capture frame with compliant mounts absorbs small impacts. Once secured, a cover extends to create a sheltered connection. Pressure and chemical checks confirm that the interface is clean. Power and data links are engaged and internal handling begins. Waste cassettes, spent filters, and used coatings move out along the reverse path and are sealed for return. Crew transfer uses small pressurized craft that carry docking collars compatible with the platform. Schedules avoid periods with expected electrical storms or strong shear. Surface interaction for science and sampling occurs by dedicated probes rather than by routine crewed work. Surface probes drop from the platform in protective shells and operate for limited hours or days, using high-temperature electronics and thermal buffers. Data uplink uses relay balloons or direct links to the platform when geometry permits. Retrieval of surface samples for return to the platform is not assumed because it would require ascent through hot, dense gas and handling of materials that may carry reactive residues. If retrieval is essential, capsules with sealed cores ascend on balloons to the temperate layer, where they are intercepted by drones with winches and brought to a sealed glove box for processing. Manufacturing at altitude remains limited. Small machining, additive manufacturing with metals and polymers, and electronics assembly are feasible inside clean, dry compartments. These capabilities support repair and limited customization. Heavy processes such as smelting, large-scale polymerization, and glass making are deferred to Earth or to orbital factories because of the need for precursors and the difficulty of protecting equipment from acid and ultraviolet exposure. Coating renewal and composite patching are routine. Spray booths with filtered exhaust and reclaim capture overspray and solvents. Cure schedules include UV shielding and temperature control. Safety and redundancy drive geometry and routing. Pressure shells are segmented with hatches and isolation valves. Fire zones are defined and separated by bulkheads with thermal insulation. Vertical separation between living decks and machinery decks reduces noise and hazard coupling. Escape routes from any cabin to a safe room remain clear, short, and marked. Safe rooms carry independent air and water for at least 1 day, and a direct communication link to the control room and to orbit. Every critical function has at least 2 independent units, separated physically to avoid common cause failure from a single leak or fire. Scaling from one platform to a cluster requires traffic control, shared maintenance assets, and common standards. A cluster includes at least one power-rich platform with a reactor and large radiators, one logistics platform with docking capacity and storage, and one science and medical platform with laboratories and care facilities. The cluster follows a planned track in the wind field with relative spacing maintained by altitude control and small thrust. Work shifts and maintenance rotations move crews among platforms by short flights. Standards define connector types, module sizes, docking ring geometry, and software interfaces to allow sharing of spares and tools across the cluster. Shared relay nodes in orbit handle communication and navigation. Integration with orbital infrastructure improves resilience. A depot in a near-polar or near-equatorial orbit stores propellants, water, and spares. Tankers cycle between Earth and the depot. Ascent vehicles from the atmosphere rendezvous with the depot, deliver data and samples, and return with cargo. The depot also hosts a service bay for inspection and repair of ascent vehicles between flights. A navigation service in orbit broadcasts timing and ephemeris that platforms use for localization and wind field estimation. Coordination between orbit and atmosphere follows pre-planned timelines with margins for delay. Construction timelines reflect the need for validation at each step. A Pathfinder platform proves long-duration materials and coatings, validates thermal and power balances, and refines lightning and corrosion protection. A second platform adds crewed operations for short tours and a small production capacity for oxygen. After both demonstrate stable performance across long day-night cycles and variable winds, a logistics platform joins and enables more complex operations. At every stage, the number of exposed moving parts and the frequency of exterior work remain minimized. If scaling introduces a need for long outside tasks, the plan adjusts by moving functions inside sheltered bays or by adding drones and teleoperation options that keep people inside. Taken together, these transport and architectural choices show a practical shape for activity at Venus. Vehicles enter through heat and drag to reach the temperate layer, where buoyancy, masts, and sealed gondolas support operations. Ascent is possible with small rockets staged at altitude and serviced inside hangars. Construction relies on modular, acid-resistant elements and on robotics that reduce suit time. Logistics chains link orbit and atmosphere with repeatable procedures. Safety comes from segmentation, redundancy, and clean-dirty separation. Even with these measures, the design remains maintenance-heavy and dependent on imported hydrogen, specialized coatings, and high-reliability hardware. This dependence sets the frame for the next analysis, which examines economics, risk, and legal constraints, because recurring costs, failure probabilities, and policy limits determine whether any of these architectures can be sustained beyond demonstration scale. Economics, risk, and law set the outer limits for any long-duration activity at Venus. The full cost picture uses a life cycle view that includes design, test, launch, cruise, capture, entry and deployment, platform operations, maintenance, resupply, crew rotation, and end-of-life disposal. Launch and transfer costs dominate early phases, but recurring operations, maintenance, and spares become the largest items once platforms are active. Mass to low Earth orbit is multiplied by transfer stages and by thermal protection for aerocapture. Mass that must survive acid, ultraviolet, and wind is multiplied again by coatings, shielding, and redundancy. Every kilogram of water makeup, hydrogen, bases for neutralization, filters, and sacrificial films becomes a steady stream in the logistics plan. Energy systems, radiators, and washdown equipment add capital cost and create recurring consumption. Supply lines are slow and lumpy. Efficient windows between Earth and Venus recur on a cadence of many months. Higher energy trajectories can shorten waits but increase propellant and risk. Hardware must be stocked with safety margins that cover delays and off-nominal events. Inventory buffers include oxygen, nitrogen, water, food, batteries, filters, seals, valves, and electronics modules. Spare aeroshells, envelopes, and radiator panels are staged in orbit and atmosphere. Each buffer ties up capital and adds storage mass. Consumables burn rates increase during maintenance and during electrical storms, which raises the minimum credible stock level. The result is a working capital requirement that does not fall with experience as quickly as on low Earth orbit programs. Power costs drive most other costs. Solar above the densest clouds reduces array area, but encapsulation and cleaning systems increase unit price and maintenance. Wind adds variability and vibration control. Compact fission gives steady output, but reactors require shielding, specialized handling, and large radiators with acid-resistant features. Heat rejection hardware is expensive per kilowatt and degrades under droplet fouling and ultraviolet exposure. Electrical storage sized for multi-day outages adds mass and replacement cycles. When energy is routed to oxygen production, electrolysis stacks and hot balance of plant double the maintenance burden. Attempted in situ resource use beyond oxygen, such as water from sulfuric acid or fuels from carbon dioxide, adds high-temperature reactors, separations, and corrosion-proof piping. These units increase electrical load and create new failure paths without reducing imports enough to close the economic loop. Labor is a scarce and expensive resource. Crew hours are divided between inspection, cleaning, coating renewal, filter changes, radiator recovery, washdown recycling, diagnostics, and core habitat tasks. External work in suits is slow and limited by decontamination cycles. Teleoperation helps, but robots also need maintenance, spares, and protected bays. Training costs remain high because the skill mix spans life support, electrical, mechanical, high-temperature process, and medical operations. Automation reduces routine load but increases the need for software assurance and for testbed capacity that reproduces the coupled environment. Personnel rotation across long transfer times requires duplicate crews and increases transport and habitation footprints. Revenue and return pathways are narrow. Science return is strong but does not generate cash flows that scale with platform size. Technology demonstration yields valuable data on acid-resistant materials, high-temperature electronics, autonomous maintenance and thermal management. But those benefits are indirect and diffuse across suppliers and agencies. Tourism is not credible under current hazards and logistics. Resource export lacks a market because accessible volatiles and metals are not present in forms that can be produced and shipped at competitive cost. Data services and remote sensing from the atmosphere do not deliver unique products unavailable from orbit. Without a buyer for bulk outputs, expansion relies on public funding or on long-horizon strategic programs rather than on commercial returns. Risk is assessed with event trees, fault trees, and probabilistic timelines. Hazards include corrosion breach at critical joints, lightning-induced surges, power loss during long dark periods, radiator fouling beyond cleanable limits, acid carry-in through an airlock, hydrogen or oxygen leak in machinery bays, envelope damage from debris or fatigue, electrolysis stack failure, control network partition, human error in maintenance, and medical emergencies. Each hazard has an initiating frequency, detection latency, progression rate, and mitigation barrier. In many cases, progression outpaces evacuation because transfer to orbit and Earth is slow. Acceptance criteria therefore require on-site restoration to a safe state with stocked parts and tools. Where single-point failures cannot be removed, physical separation and passive barriers replace reliance on fast intervention. Corrosion and fouling create a special class of cumulative risk. Failure does not occur as a single event, but as a drift toward degraded performance followed by a threshold crossing. Coating pinholes spread, hydrophobic finishes lose function, filter differential pressure rises, heat exchangers lose capacity, and cable jackets crack. Monitoring must detect trends early with thickness gauges, optical transmission checks, pressure drop logs, and thermal balance audits. Maintenance windows must open before margins are consumed, and water and neutralizer stocks must be sized for the work. If cleaning cannot keep up with accumulation during extended dark or storm periods, risk rises system-wide at once. This coupling increases the chance of common cause failures and demands conservative scheduling and spare capacity. Model uncertainty remains material in key places. Cloud microphysics, ultraviolet absorber variability, lightning rates, long-period wind shifts, and acid deposition patterns are not fixed constants. Conservative design uses worst-case envelopes, which raises mass and cost. Aggressive design can miss the true long-tail behavior and face simultaneous overloads. Reliability growth requires long dwell in the actual environment with instrumented test articles. Until those datasets exist, economic plans carry uncertainty bands that make private financing unlikely and push programs into demonstration mode rather than expansion. Insurance and financing reflect these risks. Third-party liability for launch, transit, and planetary operations must be covered under national and international frameworks. Premiums rise with unproven hardware, nuclear power sources, and long evacuation timelines. Hull insurance for platforms is expensive because damage modes combine chemical attack and weather. Lenders and public sponsors expect staged gates with hard exit points and deorbit or disposal plans. Contracts must address cost growth driven by environment-induced maintenance that cannot be forecast with standard learning curves. Performance incentives align with uptime, safe operations, and data return rather than with expansion. Governance and law define permissions, responsibilities, and limits. The Outer Space Treaty frames activities as peaceful and for the benefit of all countries. National appropriation of planetary territory is not allowed. Actors remain responsible for national authorization and continuing supervision of non-governmental entities. Liability for damage on Earth and in space follows the Liability Convention. Objects must be registered under the Registration Convention. Rescue duties in the Rescue Agreement apply to personnel in distress. Nuclear power sources require authorization under national law, safety analyses, and notification procedures. Frequency use requires coordination through international spectrum management, and equipment must not cause harmful interference. Planetary protection policies apply to biological contamination. Even without known life, standards require control of forward contamination and of unintended biological release from habitats. Environmental ethics and policy extend beyond existing treaties. Large-scale chemical release into the atmosphere, active modification of cloud chemistry, or dispersal of aerosols for terraforming would impose global changes with uncertain outcomes. Consent mechanisms for such actions do not exist at present, and international acceptance is unlikely. Even small-scale releases during routine operations must be captured, neutralized, or contained with documented procedures. End-of-life disposal for reactors, electrolyzers, and contaminated structures must avoid long-term drifting debris and uncontrolled sinking into lower, hotter layers where tracking and passivation are not possible. Safe shutdown and controlled descent to destruction or retrieval to orbit and transfer to a graveyard trajectory must be designed in from the start. Jurisdiction, contracts, and crew law require clear rules. Criminal and civil jurisdiction follows registration and national frameworks, with company policies aligned to labor, safety, and medical privacy standards. Dispute resolution mechanisms must function with communication delays. Data rights and export controls constrain the sharing of high-temperature electronics designs, coatings, and nuclear equipment details. Compliance programs and technical assistance firewalls add cost and schedule. Software used for safety-critical control must meet formal assurance standards with configuration management and change control that survive long missions and crew turnover. Audit trails, tamper-evident logs, and cyber resilience are required because remote compromise could align with physical hazards. Decommissioning and exit strategies prevent stranded risk. Each platform needs a defined end-of-life path, including fuel drawdown, waste solidification, decontamination of surfaces, recovery or controlled destruction of radiological materials, and disposal of pressure vessels. Contracts must fund these steps while the system still operates, not after failure. Orbits used for depots and relays require debris mitigation and station keeping plans. Atmospheric platforms require procedures for controlled venting and scuttling that do not produce hazardous fragments or long-lived contaminants. When compared to alternatives, the economic case remains weak. Low Earth orbit stations enjoy short logistics, fast crew rescue, and commercial markets in Earth observation manufacturing research, and tourism. Lunar bases have simpler thermal and chemical environments, and growing ties to cislunar infrastructure with water ice as a driver. Mars presents different hazards but offers local water and less aggressive chemistry. In each case, the ratio of recurring maintenance to productive output is lower than for Venus cloud platforms. Without a unique high-value output or an overriding strategic mandate, funding flows to less hostile venues. Risk mitigation can produce safe demonstration programs with defined scope. A sequence of uncrewed and short crew missions can validate coatings, radiators, electrolysis stacks, lightning protection, and logistics procedures. These missions build a dataset that narrows uncertainty and supports technology transfer to harsh terrestrial industries. They do not change the core economic balance for mass relocation. The combined weight of recurring maintenance, energy and water constraints, slow logistics, liability exposure, and international limits on environmental modification argues against settlement at scale. In summary, the economic engine is weak, risk is high and coupled, and legal and ethical boundaries are tight. A sustainable business model does not form under these conditions. Publicly funded science and technology demonstrations are viable and valuable, but they do not evolve into self-supporting colonies. The path to the final part lies in framing hypothetical solutions with clear limits, stating what breakthroughs would be required, and showing why, even with optimistic advances, mass relocation to Venus remains out of reach for the foreseeable future. This final part reviews hypothetical solutions, states the limits that bind them, and defines the conditions under which a different conclusion would become credible. The reference point remains a stable, multi-generational presence of large populations without continuous emergency support from Earth. Proposals are considered as engineering programs with inputs, processes, outputs, and failure modes rather than as single inventions. Cloud-level habitation is the most discussed path because pressure and temperature near 50 to 60 kilometers are closer to terrestrial values. Long-duration aerostats reduce some constraints but do not eliminate the main blockers. Gas enclosure lifetimes must be measured in decades with minimal patching in an environment of acid aerosols, ultraviolet light, lightning, and persistent shear. Helium leaks through polymer skins and is scarce. Hydrogen reduces mass and cost but raises flammability and handling risk. Multi-cell envelopes limit single-point failure but multiply seams, valves, and inspection lines. Gondolas concentrate crew, power, and maintenance bays in protected volumes. All exterior interfaces remain subject to corrosion and fouling. Routine operation requires a continuous program of washing, neutralization, coating renewal, filter exchange, and radiator recovery. Industrialization at altitude remains narrow because precursors for fluoropolymers, noble metal coatings, and high-grade ceramics are not present locally in usable form. A fleet of platforms improves redundancy but increases collision avoidance, rendezvous scheduling, and common cause risks during long dark periods and electrical storms. Even with reliable station keeping by altitude selection, mooring between platforms is not stable over long spans because wind layers shift and fatigue accumulates in lines and fittings. Under these constraints, cloud habitats function as research and technology demonstrators, and as short-tour crewed stations rather than as foundations for large-scale relocation. Terraforming proposals seek to change boundary conditions rather than to work within them. Global sunshade near the solar Venus L1 point would reduce insolation and allow the atmosphere to cool. Cooling would have to be sustained for centuries to millennia to alter deep thermal structure and to test whether carbon dioxide could be condensed or sequestered at scale. A sunshade of planetary cross-section requires precise station keeping in a variable solar wind, long-lived reflective or diffractive surfaces, continuous debris management, and a governance system capable of funding and operating the asset without interruption across many generations. If the shade fails or degrades, the atmosphere warms again. The engineering burden and institutional requirements exceed those of any existing infrastructure program. Chemical sequestration of carbon dioxide into carbonates or elemental carbon has also been proposed. Binding atmospheric carbon into stable solids at planetary scale requires reactive metals such as calcium or magnesium in amounts comparable to a significant fraction of the CO2 mass. Importing those metals from asteroids or other planets would require sustained transport of material masses that are orders of magnitude beyond foreseeable launch capacity. Extracting and moving the same elements from the Venus surface would demand mining and processing in the hot, dense lower atmosphere and would place critical steps back into an environment that has already been shown to be hostile to continuous machinery. Catalytic photochemistry offers a conceptual route to breaking down CO2, but any practical process must tolerate acid aerosols, ultraviolet variability, and trace contaminants while operating across the full atmosphere with controlled byproducts and energy input at terawatt scales for centuries. Water addition appears in scenarios that aim to neutralize sulfuric acid clouds, establish a hydrological cycle, or dissolve and transport chemical species. The limiting input is hydrogen. Importing hydrogen from icy bodies or the outer planets and reacting it with atmospheric oxygen or carbon dioxide would produce water. But the required mass flow is enormous even for modest changes in composition. Storage, distribution, and loss control for added water would be needed in a hot, convecting system with high ultraviolet flux. If the hydrogen source is bound to an interplanetary supply chain, the program is vulnerable to interruption. Without a durable local hydrogen source, water addition does not close as a permanent transformation. Artificial magnetospheres and radiation shields are sometimes included as enabling infrastructure. Below the cloud tops, ionizing radiation is not the dominant hazard. A magnetic shield does not address acid chemistry, water scarcity, heat rejection, or ascent energy. Investment in such a system would not change the main blockers identified in earlier parts and would not shift the feasibility of relocation. Intermediate concepts attempt staged presence with stepwise growth. A sequence can be defined that moves from uncrewed platforms to short-tour crews, to a small cluster with limited industrial functions, and then to larger clusters with shared logistics and medical capacity. At each step, failure envelopes must remain inside the ability of on-site crews and stocked spares to restore safe operation. Scaling increases area to be washed and inspected, lengthens coating renewal cycles, raises filter and radiator inventories, and multiplies battery and electrolyzer stacks. Water makeup remains tied to imported hydrogen or to high-temperature processing of sulfuric acid. Ascent vehicles and propellant storage increase fire and oxygen handling risks in machinery bays. The result is a system that grows in complexity faster than it grows in autonomy, with maintenance hours increasing per capita and with energy per resident rising rather than falling. Orbital habitats around Venus remove acid and lightning, but keep dependence on imported volatiles and on ascent and descent vehicles for atmospheric science. Solar power is abundant above the clouds, and communications are simpler, yet materials for large orbital structures are not available near Venus in accessible quantities. Asteroidal resources would need to be brought to Venus orbit, at which point the rationale for choosing the Venus gravitational well over other solar orbits weakens. Orbital habitation around Venus becomes a separate project with its own logistics and does not convert into settlement of the atmosphere or surface. For cloud habitats to become plausible foundations for relocation, specific breakthroughs would be required. Envelope materials would need self-healing against pinholes and cracks, low permeation for hydrogen or helium, resistance to concentrated sulfuric acid and ultraviolet light, and fatigue performance that supports decades of cyclic strain without replacement. Coatings would need in-situ regeneration with low water use and without large chemical stocks. High-temperature electronics would need to reach integration levels and reliability comparable to modern silicon while operating above 300 degrees Celsius, with passive components and packaging that match that endurance. Radiators would need surfaces that remain clean under droplet showers and recover performance with minimal wash cycles. Electrolyzers, membranes, catalysts, and separations for oxygen from CO2 and for water recovery from acids would need to run for years between service without loss of efficiency in the actual aerosol environment. Reliable compact fission systems with high specific power and long refueling intervals would need to be fielded with radiators and shielding tailored to acid exposure and lightning. A low-cost, high-throughput hydrogen supply chain would need to be established, or a local hydrogen source would need to be found. Each of these items is a major program. The full list would have to succeed together to shift feasibility. Even with optimistic advances, large-scale environmental modification remains a multi-century, multi-terawatt undertaking with uninterrupted governance and finance. Risk from program interruption is structural because partial progress can leave the atmosphere in a different but still hostile state, and because maintenance burdens do not pause when funding pauses. International law and consent mechanisms would have to evolve to cover interventions that change an entire planet's climate and chemistry. Liability frameworks would need to allocate responsibility for unintended outcomes across generations. Research priorities that improve knowledge without committing to relocation are clear. Long-duration aerosol and ultraviolet exposure trials for coatings, fabrics, and electrical insulators should be run at altitude with full environmental coupling. High-temperature electronics should be matured in complete sensor and control loops, rather than in isolated devices, with service data recorded over years. Electrolysis of carbon dioxide and thermal decomposition of sulfuric acid should be tested in pilot plants that include realistic aerosol filtration and neutralization chains. Lighting statistics and electrical environment characterization should be extended with distributed instrument packages. Autonomous inspection, cleaning, and patching methods for large flexible surfaces should be demonstrated. Each of these programs has terrestrial spillovers and can be justified without a relocation goal. A practical end state for the current century is a set of reliable, crew-visited atmospheric platforms that deliver science and technology data, mature materials and electronics for harsh industries, and develop procedures for safe operations in acid aerosols and strong winds. These platforms can host short tours, prove maintenance concepts, and retire uncertainty in key parameters. They do not evolve into self-sustaining cities without the breakthroughs listed above, and without a parallel solution to water and hydrogen logistics. The conclusion follows directly from the constraints. Venus offers a narrow altitude band with tolerable pressure and temperature, surrounded by chemical aggression, scarce water, strong winds, lightning, and difficult heat rejection. Surface operations remain short-lived without exotic electronics and heavy thermal management. Power is available but maintenance heavy. In-situ resource use beyond oxygen from carbon dioxide is narrow and energy-intensive. Logistics are slow, lumpy, and vulnerable to delays. Economics do not close for commercial outputs, and legal and ethical frameworks limit large-scale environmental interventions. Under these conditions, mass relocation to Venus is not feasible in the foreseeable future. Valuable science and technology demonstrations are possible and worthwhile, but they do not change the outcome for settlement at scale. This video has defined relocation as long-term, self-sustaining residence, and has followed that standard through all parts of the analysis. Basic parameters, atmospheric chemistry, and surface conditions were established. Limits for materials and electronics were described. Energy supply and narrow local resource use were outlined. Human life support, platform construction, and transport were detailed. Economic factors, risks, and law were assessed. Hypothetical solutions were reviewed with the breakthroughs they would require. The combined result is clear. Venus offers only a narrow altitude band with tolerable pressure and temperature, surrounded by harsh chemistry, scarce water, strong winds, lightning, and difficult heat rejection. Power is possible, but maintenance heavy. In-situ resource use beyond oxygen from carbon dioxide remains narrow and energy-intensive. Logistics are slow and vulnerable to delay. Commercial returns are weak, and international limits constrain large-scale interventions. Under these conditions, mass relocation is not feasible in the foreseeable future. A practical near-term path remains. Reliable atmospheric platforms can support valuable science and technology demonstrations, improve materials and high-temperature electronics, and refine safe procedures for work in acid aerosols. These efforts deliver useful knowledge without claiming settlement. Thank you for watching. If this overview was helpful, please like and save the video. The topic is complete.